All right, so I guess we are ready now. Yeah, so today we are very happy to have Fiona telling us about exact models of many body quantum scars. Go ahead, Fiona.
Yeah, thanks, guys. So I'm here for this academic year on sabbatical, and happy to talk to anybody who's interested about this more offline, if I spark your interest. And so, okay, so I understand that there has already been a talk from prior to my arrival about quantum scars, but I'm gonna sort of start from the beginning and spend some time telling you what is this quantum scar and why I think they're interesting. And so in order to put that in context, I wanted to start with a brief review of how, so I'm a condensed matter physicist, and I wanted to start with a brief review of how we in condensed matter sort of classify and think of the dynamics of closed quantum many-body systems. And so, the kind of questions that are very interesting, and I think increasingly interesting now as people become, very interested in how to maybe protect information in some way in quantum mechanical systems are, so I have a generic or some quantum many-body system. How does it, come to thermal equilibrium or not as it evolves in time? And in particular, you might be interested in knowing whether there can be systems in which some of the information is not lost, even if you're at sort of finite temperature. And so when we think about the possibilities for these dynamics, I'd say there's sort of broadly speaking, three different categories. The first category, which is the one that has been, I think, well understood the longest, is that the system will always thermalize, as long as you start in a state with some finite temperature. And so, for those of you in the high energy community, my understanding is that this is where a lot of the, kind of things that interface with interesting high energy physics sit, right? So ADS-CFT, and maybe you have a model with a black hole and that has some kind of finite temperature and is thermalizing, and the whole story of sort of scrambling and Lyapunov exponents and how entanglement grows very fast is all a story about what we would call thermal systems. And let me just say a couple of words, because this will be relevant later in the talk, about how we understand that happens. So I did feel obligated to include some kind of space-time singularity in my talk, so here it is. So the question that you might have is, I have a closed quantum system, maybe it's the universe, right? And I let it time evolve, and after a while, I observe, and maybe it starts in an eigenstate of the system, right? So, some state which globally does not have, a growth of entropy. And so how is it that after some time I observe thermodynamics? And the answer, and this dates back to a bunch of work from the 1990s by primarily Deutsch and Schrodnicki. And the answer is that, when you study the physics of your part of the universe, you're not measuring the entire universe. You're just looking locally. And so if you believe that eigenstates of a system at finite energy density look basically pretty random, then it's quite natural actually to get out thermodynamics. Okay. And so how do we sort of understand that? Well, your local system is some small subsystem A in the big universe B, okay? And so when we're measuring local properties, those are really sort of defined by the reduced density matrix of subsystem A. So I take some pure state of the whole system, okay? But then I'm gonna trace out all of the degrees of freedom in B. And now the statement is that, how can my closed quantum system be thermal? Well, it certainly will be thermal if whenever I pick some, eigenstate of the system, rho A basically looks like a thermal density matrix, okay? So this is known as the eigenstate thermalization hypothesis. And this in particular implies that any observable that I measure just in my own little subsystem A is going to look thermal. Okay, and again, whenever I say eigenstate here, I really mean any eigenstate with finite energy density. Okay, so very low energy states, the ground state, for example, does not typically behave this way. Does not ever behave this way, basically. And similarly, the entanglement entropy of this reduced density matrix of A is extensive in the size of A, so this has some kind of volume law entanglement. Okay, and so for an observer in A, if this is true for the reduced density matrix of any eigenstate, then everything is going to look thermal all the time. Okay, so these systems always thermalize. And this, I think is kind of the most generic case. In other words, to not have this happen in a interacting many body quantum system typically means you have something a little bit special. But we know that there are quite unusual special things that can happen. So in particular, we know that there are cases where the system will never thermalize, right? So, this pattern obviously is going to go away at some point, but it's a little bit like you pour your cream into your coffee and it just kind of sits there in this lovely swirly pattern, forever. And I'm not going to say very much about this because it's not really the focus of my talk, but there's two classes of systems for which we know this to be the case. The most extreme is what we call many-body localization, which is to say that in quantum systems with enough disorder in them, even in the presence of interactions, at least in one dimension, okay, we know that you can have a situation where basically the Hamiltonian has spatially local conserved quantities. And this basically means that energy cannot be exchanged between A and B, and that all eigenstates of the system fail to be ergodic. So this is kind of Schrodinger's elephant that the system never forgets. Okay. Now a second, and I think I would say more subtle kind of system that exhibits in some ways similar behavior are integrable systems, okay? So these have extensively many conserved quantities. They're typically sums of local operators. And again, this means that the eigenstates are not ergodic. This extensive number of conserved quantities prevents things from mixing with each other in a way that allows you to attain what we would typically call thermal equilibrium. And so again, these are systems that, in some sense, never thermalize. And so in both of these cases, because these are properties of, these conservation laws are properties of all of the eigenstates of the system, there's this rather striking situation, which is that generic initial conditions will fail to reach thermal equilibrium. Okay, so this is a very extreme thing, and there's been a lot of interest in this in condensed matter physics also in the last, especially in the last sort of 10 years or so. Now, the third possibility, which is the one that I'm gonna focus on today, is that the system will almost always come to thermal equilibrium, but in certain, very special initial states, it will not, okay? And so I think that there's no maybe completely universally agreed upon definition of what exact conditions you should put on something in terms of the number of non-thermal states in order to call it a quantum scar. But today I'm going to talk specifically about a class of models where I have, some Hilbert space, which is going to grow as some constant C to the L. L I should think of as the number of, so I'm going to be working on a discrete sort of maybe one-dimensional chain or discrete lattice, okay? And so L is the number of sites in the lattice. The Hilbert space size grows exponentially with this number of sites, but the number of scar states grows only polynomially, okay, with this number of states, number of sites. Okay, and so, right, and so basically, I have some non-thermal states, but the number of them is very, very small, vanishingly small in the limit of large L. Okay, And so the setup here that I'm going to specifically work with is I'm always going to work with some chain, okay? This chain is going to have some Hilbert space, which is the same on every site, okay? So I'm going to, call this a spin chain. It doesn't mean that the Hamiltonian has to be spin rotation invariant or anything, but I have 2s+1 states on each site, okay? And I'm going to label those by eigenvalues of SC. Which is just a label. Okay, so the Hilbert space grows as 2s+1 to the L, okay? And then the kinds of Hamiltonians that I'm going to think about are Hamiltonians that are strictly local in the sense that, and actually the ones that I'm going to write down today are sums of, I could have a term that acts on a single site, okay, a term that acts on site I and its neighbor I+1, okay, or terms that act on second or maybe third neighbors, okay? But these Hamiltonians are very strictly local. Okay. And okay, and so what we're going to look at to search for, to say that some of these, so I'm gonna write down a Hamiltonian, okay, of this form, and what we're gonna look at to say that some of its eigenstates are quantum scars is the following. So we're gonna have our chain, okay, well, not me, but the student, Nicholas Adea, who is working on this project, took these Hamiltonians and diagonalized them numerically, okay, and you get all the eigenstates, okay. You can cut the chain in half, okay, and you construct the reduced density matrix of the left half of the chain, okay. And you calculate the entanglement, what we call the half chain entanglement, in each eigenstate, okay. And so the typical way that, if you have a Hamiltonian, that if you wanted to kind of numerically show that these scars are there, is you would make a plot that looks something like this, okay? So on the y-axis here, we have this half chain entanglement, okay? Each dot is an, okay, and on the x-axis, we have the energy, in this case, scaled by the length of the system. This is for a single system size, okay? And each dot represents an eigenstate. Okay, so here's an eigenstate that had energy, minus 1 point something and entanglement approximately 2, okay? And what we see in a system with quantum scars is this band, this narrow band, okay, where the states in this band are very close to just the thermal entropy of the chain at that energy density, okay? But then somewhere, and if I looked at different system sizes, this curve, should grow with L, the number of sites, okay? And then somewhere far below these in entropy is some much smaller number of states, okay, which have much smaller entropy, okay? And this is a particular model. This is a set of states that we can prove has entropy that scales at most logarithmically as the system size grows. So this is the kind of picture that I'm gonna draw when we talk about many body quantum scars. And so this gives you a picture of what's going on. You can really see a band of thermal states, okay? And there are a lot of them, there are exponentially many of them, and then this very tiny number of scar states. And these are all eigenstates of the Hamiltonian.
For large L, would your band of thermal states become arbitrarily sharp?
Yes. Yeah, that's right. So the fluctuations, there's statements in the eigenstate thermalization hypothesis that control the magnitude of the fluctuations about these, about these values. And so certainly for local operators, those fluctuations fall off as 1 over the square root of the entropy. For entanglement, I'm actually not sure if that's sort of proven, but that's certainly, if you look at the numerics, that's certainly what happens, and certainly expected.
Okay, thanks.
Cool. Yeah. Okay, so this is the idea of the quantum scar. This is a phenomenon that that is interesting. And so let me just sort of say what my objectives are for the rest of the talk. So I've shown you a plot, which spoiler alert, we do have Hamiltonians where we can find exact eigenstates that have this funny property that they are what we call quantum scars. And so now I want to sort of address 3 questions. The first one is just why should you care? okay? The second one is, what kind of structure can we kind of understand when this happens, what structure is associated with it, how do we build, new models with these features? And then the third question is, how sort of special is this? How hard is it to find a system that has quantum scars? So let me start by addressing the obvious question, which is, why should I care? And so I say this is an obvious question for the following reason, right? So I have these scars, and it's true that, if I manage to start my system just in this little tiny scar manifold, then it's gonna exhibit some pretty interesting non-thermal behavior. But to play devil's advocate, you might say, this is such a tiny number of states. It's a set of measure 0 in the limit that L gets to be, large, kind of some lab scale thing. So honestly, why would you care? Why would you expect that you can ever see something like this? And the answer is that we, at least in some cases, it just so happens that experimentally accessible states appear to be able to have, quite a large overlap with this tiny scar subspace. And so the thing that actually got people really interested in this field was actually an experiment. This was an experiment out of Misha Lukin's group at Harvard. And the details are not important at all, but basically they have a chain. It was a fairly small chain. It was about 51 or 52 atoms, okay? And each atom is some two-state system, so I'll call it, up and down, okay? And they can make this in their lab, and it's easy for them to prepare a specific product initial state. So they prepare the product initial state down, up, down, up, down, up, down, up, okay? And there's some Hamiltonian, again, details are not important for our purposes, but they prepared this initial state, and then they just let their system evolve under that Hamiltonian. And I should say that under that Hamiltonian, this state here is a very high energy density state, okay? And what they saw was actually these long-lived, you can see they're not infinitely lived, but these long-lived oscillations, okay? And this was actually very surprising because, as I said, the initial state that they were studying corresponds to a very high temperature configuration. And so what you would expect is basically, very rapid relaxation to some thermal state, okay?
Excuse me, does MPS stand for matrix product state?
Oh, oh my goodness, actually,
And I mean, this is actually, I asked that because I've been wondering if matrix product states are a useful way of making quantum scar states.
yeah, so in this case, I apologize. I actually do not remember what MPS stands for. I do not believe it's matrix product state in this case. This is some kind of, model that they're fitting to.
Okay.
Yes, I don't believe it's a matrix product state model, but I apologize. I actually don't remember exactly what they fitted to.
But that's not where you're going in the talk.
So I will come to matrix product states at the end, and I absolutely do think that there's an interesting connection there.
Okay.
But at this point, yeah, that's maybe not so relevant to what I want to say about this particular experiment. Yeah. Okay. Right, and so then the conjecture, and this was put forward by a paper, kind of posted in 2017, published in 2018 by Turner et al., where, so a theory paper, okay, where they proposed that, maybe what's happening here is that this Hamiltonian has or is close to some model that has quantum scar eigenstates, and that this initial state has, actually large overlap with quantum scars. And they presented some numerical evidence for that in finite size systems. I would say that, actually for the particular Hamiltonian relevant to these experiments, that debate is still not entirely settled, but I think this, at least illustrates this possibility, or got people thinking about this possibility, that there could be laboratory accessible initial conditions where you can really observe this very surprising non-thermal behavior in a system which is not integrable and not localized. Okay, so in other ways seems quite generic. Okay, and so that's why, at least in the condensed matter community, people started thinking about this very seriously, which is to say that even though this set of scar states can be very small, we can construct very simple, potentially laboratory accessible initial conditions where that live entirely in this scar space. And I'll show you later at least one example of why that's not so hard to do in some of our models, where you could actually observe this highly non-thermal dynamics. Okay. All right, so now let me give you one version of, what is the structure underlying certain kinds of scar states, and correspondingly a recipe for how to find them. Okay. So one kind of structure, and I'm not going to claim at all that this is universal, but one kind of structure that can give rise to scar states is if you start from a Hamiltonian with a non-abelian symmetry. So I'm going to consider Hamiltonians of this form. Okay, so I have some piece, I'm going to call it HC, and this piece is going to have some kind of non-abelian symmetry. Okay, and I'm also going to have a piece that I call HS. HS is not very important, but its role is simply to ensure that the scars are not energetically degenerate. Okay, so it's some Hamiltonian that assigns different energies to the scar states, and typically we want HS to assign one, or more generally a small number of different frequencies to our scar states, so that we can see nice periodic revivals and so on in time if we built these things in the lab. And finally, there's a piece that I'm going to call HA, and this, as we're going to see, is some kind of rather special symmetry breaking term. Okay, and its role is going to make the model look generic away from the scar subspace. Okay, and so to understand kind of how one gets scars out of non-abelian symmetry, let me just take a step back and talk about thermalization, or eigenstate thermalization hypothesis in the presence of symmetry. Okay, so obviously imagine that I have a model that has some kind of SU2 invariance, right? And so how should I treat that model? Maybe I'm a numericist and I have some Hamiltonian, and somebody asked me, hey, is this Hamiltonian thermal? Okay, and so what do I do? Well, certainly if I look for standard measures of thermalization in the Hamiltonian as a whole, it will not look thermal. Okay, and the reason is that the eigenstate thermalization hypothesis basically says that the eigenstates of your Hamiltonian should look as generic as they possibly can, given the constraint of whatever the local energy, whatever the eigenstate's energy density is. Okay, and so certainly eigenstates of a Hamiltonian with, say, SU2 invariance do not look as generic as possible, because they break into these blocks of total spin. So what I should do instead is, I decompose my Hilbert space into a direct sum of states of different total spin, okay? And then what I should look for is a Hamiltonian that's going to look thermal, right? So states within each block, if I just look at this little Hamiltonian, for example, in the S=0 sector, I would then check if those states, that small block, satisfy ETH.
So I have a question about this. So yes. I would have thought that the symmetry would be more like a global constraint on this. And so if you looked at the small portion of the system, the symmetry would not be very constraining. And
so, well, so maybe I didn't say it very clearly. All I'm saying is that, if H has SU2 symmetry, then eigenstates of H have a conserved quantity, which, which like the total spin is conserved, right? So I can break my Hamiltonian into—
That would be the total spin on the whole lattice, but the eigenstate thermalization hypothesis involves some subset of the lattice. So
good. Yeah. So yeah, that's right. So this S here is the total spin, So maybe I have a spin 1/2 chain with like L sites, right? So I take L copies of the spin 1/2 representation, right? And then I take all of the singlets that I can get out of those L copies. And that's everything that goes in here. So indeed, when I cut my system into an A and a B, it's not the case that the spin on subsystem A is conserved in these states.
I think what you'd observe, though, is that the density matrix in subsystem A commutes with the spin operator. For example, suppose the group is U1 for simplicity. Because the charge is conserved, when you integrate out subsystem B, the density matrix of system A is diagonal in the charge basis. So you can observe that it's not generic.
Right.
Why
Okay.
is the charge conserved? Why can't the charge go from A to B?
It can, but that doesn't affect the fact that the density matrix commutes with the charge.
Right. Yeah, that sounds right. Yeah, the point is there's processes that transfer charge from A to B, but if you trace over B, but the density matrix of subsystem A would still contain.
It has components of different charge.
Right.
But it's diagonal in the charge basis.
Yes. Yeah. Okay. I agree with that.
Okay. Thank you.
Does that kind of address?
Yeah, that I think is kind of
Okay.
the question.
Perfect. Okay. Yeah. So right. So this is kind of the general picture that, in terms of the total spin of my whole system, I break my Hamiltonian into these blocks, and one sort of obvious statement is that some of these blocks are small. For example, if I take my L copies of spin 1/2, right, and I look at the number of states in the representation of spin L over 2, that number is not exponentially large in L, it's only linear in L. Okay, so that block is sort of what we would call small. Okay. And so one, fairly straightforward way to get quantum scars is just to basically leverage that observation. Okay. So imagine that I start with a Hamiltonian with SU2 symmetry. Okay. So I have a spin S chain with L sites. Okay. And then I'm going to propose a candidate scar tower, which has what I'm going to call a base state. So this base state is just the state where, SC is minus S on each site. Okay. And then the other states in the scar tower are related to this base state by acting with some power of a raising operator, which I'm going to call Q dagger or Q plus. Okay. And in general, I can have a kind of momentum shift between the different sites. So I could take, S plus 1 minus S plus 2 plus S plus 3, etc. Or I could just add them all up. Okay. But I have some kind of, spin raising operator that acts on all of my sites. And this is going to be a tower of which this is going to generate, basically if I take k equals 0, this is going to generate all of the states in that highest spin representation. Okay. So let's take k equals 0 for now. And I'm going to propose these as scar states. And now we have to ask, can I find a Hamiltonian for which these really do look like scar eigenstates? Okay. So first of all, what kinds of Hamiltonians will have these as eigenstates? So obviously I can have any term in here that respects SU2 symmetry, okay? Because under, these states, this whole tower of states has to be degenerate, so they all have the same energy. So clearly I can make all of them into eigenstates, okay? And then, if Q plus is just the operator that raises the total spin by 1, then I can certainly have some term that's going to give an equal energy spacing to the scars, which is just proportional to SZ, okay? And again, because my base state was an eigenstate of SC, it had the minimal SC, I'm guaranteed that because of the commutation relation between my Q plus and SC, I'm guaranteed that all of the states in the scar tower are also eigenstates of HS, okay? And so the only non-trivial thing is, again, if the Hamiltonian just had this symmetry, I wouldn't say that it has quantum scars. I would say, you know, it has a symmetry, and those are not quite the same thing. And so I need this special symmetry breaking term, okay? And what's special about this symmetry breaking term is that I want it to actually happen to annihilate all of the scar states. Now, if I'm working in this highest total spin representation, that's actually pretty easy to do. All I need is, you know, because the highest total spin means that, you know, every, if I just look at, you know, 2 adjacent spins, they have to be in the triplet rather than the singlet state. And so anything that projects a pair of neighboring spins onto the non-maximal, you know, a pair of these spin S representations onto the non-maximal spin state, 2-site operator will annihilate all the scar states. Okay, so this is actually not that hard to do, right? And so if we put all these pieces together, we have these 3 terms in the Hamiltonian. Every scar state is an eigenstate of each one, right? And you get this scar tower, which has these evenly spaced states that can go across the spectrum, okay, with energy spacing omega. And so here it's kind of important that that there are L of them, so that we know that at least some of them are, you know, have high energy density. Okay, and so just to kind of, I think it's nice to write down an example so that you can get a picture for how simple these Hamiltonians can be. Okay, so so the idea that, you know, SU2 symmetry and highest spin representations might have something to do with quantum scars was already proposed in this original paper, although they didn't have a concrete way to relate that to the Hamiltonian they were interested in. But, you know, you can write down a number of nice Hamiltonians that have this property. This one is due to Mark, Lin, and Matrunich. Okay, so this is just some nearest neighbor and next nearest neighbor spin coupling in a spin-a-half chain. Okay, here I can add an SZ. You can, you know, always do that with a lab magnetic field if you want. And this term here is just a kind of spin-spin, sorry, there should be a parenthesis around here, but this is a spin-spin interaction that's actually quite natural if you think about materials where you have spin-orbit coupling that affects the electronic processes that are generating these spin-spin interactions. So, you know, from a condensed matter viewpoint, this is a very simple, quite natural Hamiltonian to think about, and this has actually an exact tower of quantum scars. Okay. Okay, so the moral of the story is that, you know, when I think about non-abelian symmetry, there's actually, you know, a very obvious candidate tower of scar states, right, which is some small multiplet isolated by symmetry. And in order to turn those into real quantum scars, all I have to do is basically find these non-generic symmetry breaking terms, right, that have this special property that they just annihilate the scar states, but are sufficiently ergodic to kind of, you know, mix up all of the other symmetry sectors. And often these Hamiltonians can be pretty simple.
Sorry,
okay.
should I view these Hamiltonians that have scars as special Hamiltonians, or that?
Yeah. So yeah,
the fine-tuned position and the generic one will not have them, and we were just lucky that in some systems we are close to these special Hamiltonians.
Yeah. So certainly, it is certainly the case that, you know, if I, for example, if I added a term that looked like this, but with I+1 replaced with I+2, right? So that, you know, that would be a problem. So in other words, if you say, okay, well, this Hamiltonian doesn't have any symmetry, so let me just add, you know, let me imagine that I'm coarse graining a little bit. I'm going to start adding all of the terms that are allowed. Then certainly in that sense, this Hamiltonian is very fine-tuned, right? We don't have any mechanism that we currently understand that protects, you know, this kind of special isolation of this small number of states. On the other hand, I think it's important to note that, you know, it's quite plausible to imagine that there are, you know, materials or you know, in particular these kind of cold atomic systems where people can prepare all kinds of initial states and measure dynamics very well, where actually these Hamiltonians would be a very apt description. So it's fine-tuned, but I think, you know, still interesting experimentally.
Okay, good. Thank you.
Yeah. Great. So once we understand this mechanism, we can think about a whole bunch of different generalizations. So the first thing you could do is you could choose a different sort of ladder operator. So, you know, maybe I'm not gonna just look at the total spin, but maybe I take a sum over different sites of S plus, and I raise it to some power, maybe 2S, okay? And then I can again start in this, you know, state of minimal SC and create a tower of scar states, okay? And one can write down Hamiltonians. Oh yeah, and I should say, when I write down this Q plus, okay, so this one is, if this is 2S here, these guys are associated with a new, you know, SU2 symmetry algebra, but it's distinct from spin, rotation, and variance, okay? And so the mechanism is basically the same as what I said, except for that the SU2 is not coming, you know, directly from the spin SU2. And one can write down Hamiltonians of this form, and they're actually relevant for understanding quantum scars in some, you know, models that were already well known in condensed matter physics. Okay, so that's one thing you can do. A second thing that you can do, which I personally find quite amusing, is I can actually change the symmetry group. And so, you know, if I have, say, a spin 1 chain, let me, instead of thinking of that as a spin 1 chain, just say I have a Hilbert space on each site with 3 different states. And let me treat those states as the 3 states in, you know, the fundamental representation of SU3, okay? And then I can use exactly the same philosophy to construct an example of a system that has exact quantum many-body scars. So how does that work? So my base state is going to be, right, so I'm going to take, you know, I take my L copies of the fundamental, right, and then I take the completely symmetric representation of that, and then within that representation, I pick the lowest weight state, okay? And now instead of one kind of ladder operator, I'm going to have 2 different ladder operators, okay? And instead of one SZ operator, I now have 2 different operators that live in the Cartan subalgebra, and so I can add them with different coefficients, okay? And again, there's a fairly obvious, you know, set of choices for HA, which are basically 2-site operators that annihilate, you know, configurations that are totally symmetric in 2 sites, okay? And so using this kind of philosophy, and I'm not gonna write the Hamiltonian because I don't find it particularly enlightening, but you can, you know, construct a Hamiltonian starting with an SU3 symmetric model that has these sort of towers of scar states. So psi naught again is this lowest weight state in the totally symmetric representation. And now my scar tower is actually indexed by 2 integers, n and m, telling me the power of each of these 2 different raising operators. And what you get is something quite amusing. So here is our thermal sort of band up here, right? And then each color represents a single value of m, okay? And then the different states within each color are different values of n. And so you can see that there's one frequency which tells you how far apart these, you know, these states of the same n but different m are, and then another frequency that tells you how far apart states of the same n, and the other way around, n and m, right? So I get this nice kind of picture with this much more interesting kind of structure in the tower of scar states. And so, you know, what about observing dynamics in the lab? So it's worth noting that in this model here, and this is also true for the SU2 models, although I'm not going to show the plots, you can construct very simple initial product states that have these exact periodic revivals. So in this case, so plus 0 and minus is just a basis for the 3 states on each site. Okay, so so this is, you know, spin 1, spin 0, spin -1, but you could equally well think of these as red, green, and blue, okay? And so this is just a product state, you know, of a particular linear combination of these guys on each site, okay? So again, this is a state that, you know, you could imagine in some kind of cold atom experiment, you could potentially imagine preparing in the lab. And you can see that depending on the particular, and I've left out the normalization here. So depending on the particular linear combination you take, you can construct states that have this kind of simple periodic revival in time, or you can construct states that have this more complicated revival structure where you see multiple, where you really see the effect of both frequencies, okay? But the important thing is that, you know, because this is an initial state that lives entirely in the scar subspace and the scars are exact eigenstates of the Hamiltonian, this, you know, these periodic patterns will continue forever. These systems will never, these initial configurations will never thermalize. Okay. And one final generalization, which is, I think, amusing to people who like to think about integrable systems, is you can also use the same philosophy to replace your symmetry by what we call a Q-deformed symmetry. So we specifically looked at Q-deformed SU2, although we believe that this works, you know, more generally, but the representation theory is more complicated. So, you know, what is a Q-deformed symmetry? Well, it's basically that you take SU2 in our case, and you deform the commutation relation of Q plus and Q minus, okay? And basically, this means that if I want to construct an operator that looks like Q plus across many sites of the chain, rather than just adding up Q plus on each site I have to multiply that on each side. So here, you know, there's a product of all of the sites to the left and a product on all the sites to the right of this, you know, this factor of Q to the minus capital QZ, okay? And there's, yeah.
What is that E to the IKR doing?
Oh, good. Okay, yes. So far, E to the IKR hasn't entered into our discussion very much. In all of the models that I'm aware of where the Hamiltonians look nice, K is either 0 or pi, okay? So this is useful because sometimes, for example, choosing K equals pi, not so much in this class of models, but sometimes choosing K equals pi will give you a more physically appealing Hamiltonian because this K will affect what your choices of HA are. So, and you can see that, you know, if you think about like the maximally, if you think about the SU2 example, right? If I chose this to be 0, then I'm always looking for like the symmetric combination, and that's the one where HA is kind of obvious. If I chose it to be pi, in that case, I have to be a little bit more careful, you know, to annihilate the right thing. Oops. Does that answer your question?
Yes, but just for the symmetry, could you have used any K?
Yes. Yes.
Okay.
Yes, I could have used any K. But
you don't get such a nice Hamiltonian.
Yeah. Those Hamiltonians don't look very physically realistic, let's say. Yeah, so I can, right, so I can, you know, use this, so this Q-deformed symmetry has, you know, very sort of qualitatively similar representation theory. And, you know, I think the details aren't so important, but you can basically play the same game. You have a lowest weight state, you can generate a scar tower, and you can actually take, you know, a Hamiltonian that works for ordinary SU2 and basically Q-deform the operators, okay? And get something which again has these Q-deformed quantum scars. Okay, so all of this is to say that, you know, basically when we think about symmetry, whether it's SU2 or some larger Lie group or even Q-deformed symmetries, there's actually a very natural mechanism to think about where scars come from. They come from, you know, starting with a model that has that symmetry and then breaking it, but doing so in a non-generic way. Okay. And once you understand this general structure, you can, construct all kinds of examples. And, I think a nice thing is that at least some of these examples look very natural, as models of realistic physical systems.
Can I think of this as in the following way? So we imagine we could have a system such that for some states there is an approximate symmetry, right? But not for generic states. So as an approximate symmetry that emerges when you consider certain special states. So here in your case, that symmetry might have been SU2 and the special states were the scarce states. I mean, in your cases, it was exact, but let's say we have some approximate scars. So for an example would be, imagine you have a fluid, right, in 3 dimensions. And so everything interacts with everything else, but imagine you separate the fluid into 2 droplets.
Okay.
And then each droplet, for example, could rotate independently from the other. Mm-hmm. So in that case, you have like an SU2 symmetry, which acts on each droplet separately. And the terms that break the symmetry would be very small for these states. They would not be small for when the droplet is forming a whole.
Oh, I see. Yeah.
So
Yeah. No, I think. Yeah. So certainly, so let me just to try and paraphrase. So I think if what you mean by an approximate symmetry on some states is the idea that I think the important thing is there's some kind of conservation law, right? Mm-hmm. But that conservation law kind of only applies in
some states. Yeah, that's the idea.
No, and I think philosophically that's exactly the mechanism.
Because I think this is this is very common, right, in systems of having. Well, this example of the rotation is a simple example. But.
Yeah, that's a nice picture.
Okay.
Yeah.
Thank you.
Yeah.
I'm thinking about your general philosophy. I mean, what's really not, that clearly will produce examples, but what's really not obvious, but what your examples show can happen naturally is that you'll have some kind of locality if you apply that general idea.
So I think that
you could do this, pretty generally as you're pointing out in your second book.
Yeah.
But in general, that's not going to lead to any kind of nice local Hamiltonian.
Okay, so I guess the way that I view it is that you can ask a question, right? Which is, I want this Hamiltonian HA, which satisfies 2 properties. I want it to annihilate, this small corner of the Hilbert space, but I also want it plus, maybe in combination with this symmetric term, because those symmetric terms can also be important. But, I want HA basically to be generic enough that outside of the scarce space, it's going to make the system thermal. And then you could ask, can I always do that with an HA that's like local? Is that maybe a correct paraphrasing of what you're talking about?
Well, I'm just saying that, I could construct your kind of thing by taking 2 projection operators onto 2 orthogonal parts of
oh, I see.
And use then put a Hamiltonian, I could compress with 1 projection operator onto the big square, a thermal Hamiltonian, and something like that. And I could do that in a very general way.
Right. Yeah.
I have some lattice system in mind, and I'm doing that, with arbitrary subspaces of the Hilbert space. I think what goes wrong from a physical point of view is that it would be very non-local.
Okay. Yes. Very good. Yeah. I agree that the non-trivial thing. I think I would say the non-trivial thing is that you can do this in a local way. Absolutely,
that's what your examples are showing. Yes.
Yeah, there is a pretty large class of local examples which utilize the fact that scarce states can have actually a much larger symmetry than SU2.
Yes.
That's basically what the point of our paper was, that it's indeed a big concern how to do it locally, but using the fact that some scarce states have the full UN invariance or ON invariance, where N is the number of lattice sites, then it's very easy to write local HA expressions.
Yeah.
By the way, I looked up the Burdell et al. Paper, and MPS did refer to matrix products.
Oh, did it? Oh, okay.
Yeah.
So they had a matrix product state model of the.
Yeah, it was some chain of cold atoms, right? But yeah, it wasn't really like an AKLT, right? It was some simpler model, but apparently MPS was.
Thank you. Okay. So let me move on to the last question, which is, so you might want to ask, so, you know, this is one kind of picture of where scars come from. And you might want to ask, well, how, or, you know, it's one way of thinking about a structure that can give rise to scars. Let's think about that. And as Igor mentioned, there's, you know, there's kind of many pictures of that. But let me address, you know, how, you might ask in general, you know, how surprised should you be, or how hard is it to construct a model with quantum scars? And, you know, in particular, are they generically related to some symmetry? And the answer is absolutely not. So the structure that I told you about is nice, and it allows us to think about certain examples and even certain well-known examples in a kind of simple way, but it's far from being able to explain even all, you know, known models. So you can actually do something much more general. So suppose that I have an operator, I'm going to call it Q plus, okay? And this can be any sum of single site operators, or it can be, you know, any sum of these kind of Q-deformed spin raising operators that I talked about. And I wanted to have the property that if I take it, if I raise it to some power that grows not faster than polynomially in the system size, it's 0, okay? And then I'm going to start with some base state. So this is a matrix product state. And for those of you who aren't familiar with matrix product states, I mean, so these are just matrices, okay? These are translation invariant in the cases that I'm talking about. And so each A is a matrix, which, you know, if I have, say, 3 different spins, plus, minus, and 0, I get a different matrix for plus, minus, and 0, and then I just multiply all those matrices together to get the relevant coefficient of the wave function, okay? The important thing is, this is just a way of representing a state that has finite entanglement, okay? So I start with a base state that has finite entanglement, okay? And I propose a scar tower by acting with, you know, Q plus to the n on psi naught. Okay, so you can show that this will always generate a tower of low entanglement states. So this is always a good candidate scar tower. Okay, and so, you know, if I, so now I want to say, okay, here's my candidate scar tower. How do I generate a Hamiltonian for which these scar states are eigenstates? And so, you know, if I chose my base state, for example, to be an eigenstate of SC, and Q plus is something that, you know, raises the spin in some sense, then, you know, I can always choose HS to be omega SC. More generally, if I don't, you know, care too much about having evenly spaced scars, I could choose, you know, or non-degenerate scars, I could also choose HS to be 0. So HS is not too important. So the real question is, how do I find HA, right? And this is the non-trivial thing. When can I find HA that is, you know, some sum of local operators? And in fact, there's a brute force method that allows you to at least search for these guys, which is to say, so I, you know, suppose that I want my HA to be some of, you know, just nearest neighbor operators, okay? And so I pick some basis for all Hermitian 2-site operators in my system. So I'll call that O hat alpha, right? And I want to find which are my choices of linear combinations of O hat alpha, such that HA is going to annihilate all of my scar states. Okay, and you know, basically you can do that systematically. Okay, using a method, this was due to Xiaoling Qi and Daniel Reynard. Okay, and you basically construct a matrix for each eigenstate psi. So this should be psi n. Okay, and I look for the null eigenvectors of this matrix. Okay, and I in particular look for the simultaneous null eigenvectors for all psi n. Okay, and that gives me the solutions C alpha, which allow me to construct operators HA of this form. Okay, now, of course, the fact that we know how to do the brute force search does not guarantee that we will find non-trivial solutions. So you might ask, you know, do I always expect to find non-trivial solutions? And I don't, you know, have any clear statements to make on that, but the kind of general observation is that if the targeted Hilbert space is small enough, and in particular, you know, if one runs into trouble just looking at sort of nearest neighbor terms, I can always extend to sort of second neighbor terms, and that gives me many more operators here. And so it seems that, you know, at least based on our experience playing around with models, that if the targeted Hilbert space is, you know, not bigger than, say, linear in L, that that we typically find not only at least one non-trivial solution, but actually enough non-trivial solutions that we can construct some kind of Hamiltonian that looks ergodic in the rest of the Hilbert space. Okay. Now, and so the moral of this story is that although symmetry gives us a nice way to understand how some scars emerge, you know, there are certainly many models with exact scars that don't come from symmetry in this way. And one famous class of examples, let me just sort of end with this, are AKLT-like examples, okay? So the AKLT model is a famous model of the spin one chain where the Hamiltonian basically just projects onto the Hamiltonian is a projector onto a sum of projectors of two site terms. So P j plus 1 projects sites j and j plus 1 onto total spin 2. Okay, and it turns out that this model has exact quantum scars, which can be generated from the AKLT ground state, which happens to be an exact matrix product state, using this particular operator Q plus. Okay. Now, what's different about the scars in the AKLT model is that, so these are eigenstates of SC, and actually of S squared, so the AKLT model is spin rotation invariant, but if I looked at the SU2 symmetry associated with this raising operator Q, the AKLT ground state is actually not an eigenstate of Q squared, okay? So this, you know, does not live in a single symmetry multiplet, and therefore, you know, is quite different from the class of examples that I discussed before. And so you can take this AKLT model, and again, there's many generalizations of it to higher spin and Q deformed and so on. And how do we know that? Well, that's because these guys, the scars here, can be understood based on a rather different kind of structure. So these particular matrix product states that enter here have a rather special structure, okay? And I can articulate that more clearly offline if anyone wants, or afterwards if anyone is interested. But you know, this sort of special structure actually allows one to identify entire families of either either Hamiltonians with closely related scar states or actually with the same scar states. And that allows one to think about, you know, taking these models and, you know, preserving the scars and deforming them to, you know, things like highly symmetric and degenerate or integrable points and so on. So not to kind of belabor this point, but in general, I think it's fairly natural to expect that if you're looking for only order L scars in an exponentially large Hilbert space, that it's not that hard actually to construct Hamiltonians that will do that for you. And some of those Hamiltonians have a sort of different type of structure, which, you know, some of these known examples have structure that comes out of the structure of the matrix product state, which actually, you know, also, oh my gosh, allows us to, allows us, you know, is also kind of quite easy to generalize and deform. Okay, and so that's all I had to say. So, you know, I'd say quantum many-body scars, they are fine-tuned, but they're actually not so fine-tuned as to be physically uninteresting. Okay, so this is a new class of non-thermalizing systems, which I think are worth understanding because, you know, say it's not crazy to say that it can have an impact for understanding dynamics of real systems that we could make in the lab. And one way that you can naturally get them is to think of, you know, having some kind of special symmetry breaking, okay? But in fact, in general, there's, you know, large other classes of Hamiltonians that also have them. And in fact, constructing those models is maybe not as hard. They're not as exotic as you might have at first thought. And let me end there and take any other questions that people have.
All right, thank you, Fiona, for the interesting talk. Is there other question for Fiona? I actually have a quick one. So you mentioned some experiment. So in the experiment, why did they do such a fine tuning to land on a system with quantum scars?
Oh, okay, yeah. So the experiment was not fine tuned. I mean, they have like control of the Hamiltonian, but they don't have infinite control. So the proposal there, I mean, and the experiment actually, they, so I should say that the reason they were doing that experiment was not because they were looking for quantum scars. They were actually, the Hamiltonian has a very strong repulsion between two neighboring states that are up, okay? And so that actually gives you, if you take that energy scale to be very large, it gives you a Hilbert space, which is constrained, and that constraint is also relevant to people thought about models of sort of chains of Fibonacci anyons. Okay, so Fibonacci anyons are very exciting because they're universal for quantum computing. And so what they were actually trying to do was, you know, look for, you know, some kind of dynamics which, you know, due to this constraint would be related in some way to Fibonacci anyons. But what they, you know, so I think that's why they were, you know, like doing these kinds of experiments. But what they actually found was this oscillation, okay? And then the idea that this might be due to quantum scars was proposed a little bit later by a theory group. And so it is known that there are exact scarred eigenstates in that model, but but there are not exact quantum scar eigenstates that appear to be controlling that dynamics. There is a belief that, so in the original paper, they just sort of, you know, said the eigenstates maybe have like significant overlap with quantum scars. And then what was shown later is actually if you take the Hamiltonian that's believed to describe the experiments and perturb it a little bit and tune that term, then you can get to a model which has, you know, almost like numerically almost perfect quantum scar eigenstates. Yeah.
I have a question. I think you sort of just answered it, but I'll ask it anyway. Is there some sense that these quantum scar subspaces have quantum error correcting properties and are nice code subspaces?
I don't know about quantum error correction. I think certainly
I thought that was implied by what you were just saying about the anyons.
Well, okay.
My question is independent of what you said. So, so you have a nice subspace, some kind of interesting special subspace. So, you know, is it a good code subspace?
So in the sense that if you can prepare states in that subspace, they're not going to completely decohere, I would.
Oh, no, I'm thinking that you have some collection of error operators, E alpha. And you want to say that, what is it, the compression of E alpha dagger E beta is a Hermitian matrix, is proportional to the identity in alpha beta space. Well, there's a definition of what a error correcting code is. And then, so I'm wondering, you have a, you know, these special subspaces, maybe they have error correcting properties, at least with respect to some nice set of error operators.
So yeah, off the top of my head, I don't know, but there may be other people here who are probably, you know, maybe no better position than I am to address that. Because I mean, you know, in the simplest version, you just have this highest spin multiplet, right, of some non-abelian symmetry. So you could ask, is there a natural kind of error?
Oh, right, exactly. I mean, you could make a good set of error operators using the SE2 symmetry and then ask, I have no idea if it's true, but you could ask if it has error correcting properties with respect to those operators.
Right, right. Yeah, right. So yeah, off the top of my head, I don't know, but I think, you know, certainly for some of these, also these AKLT examples based off matrix product states, I mean, I think you could, I think it's an answerable question, but I don't know the answer.
Thanks.
I think there was indeed earlier literature on things related to scars, and I mean, we did mention it very briefly in our paper.
Oh,
but it goes back many years, I think, some related.
Are you thinking of Shirashi and Mori?
No, even earlier. I mean, maybe Kirill knows off the top of his head, but yeah, there is a whole branch of the sort of quantum information applications.
Okay, yeah, because the first, and actually, I didn't have it in here, but the first construction that certainly, you know, is kind of well known in the condensed matter literature was, and this predated the experiment, was there was a paper by Shirashi and Mori where they kind of pointed out a way to construct this.
Yeah, that was the PXP model, right?
No, before the PXP model. This was the observation was simply that if I take a Hamiltonian which is just a sum of projectors, right, and I add them all up with a positive. I mean, it's more they did something more general than this, but the basic idea is if I take a sum of projectors and I add them all up with positive coefficients, and the projectors don't commute, but they have you know, there's some state which they all annihilate, then that state is the ground state of some Hamiltonian. But then if you know, add them up with, say, alternating coefficients, so that state has energy 0, right, no matter what the coefficients are. And so it could be the ground state, but it could also sit in the middle of the spectrum. So that was certainly an observation that predated the experiments, and it sort of maybe didn't get a lot of attention until people started trying to understand, well, why are these persistent oscillations observed? But yeah, absolutely. And maybe there's something even before that that I am missing.
Yes, I think Isaac Chuang wrote some paper, LiDAR Chuang and somebody, called Decoherence-Free Subspaces for Quantum Computation.
Ah, okay.
I think was pretty close to these scars.
To these ideas. Okay, yeah, no, that's good to note.
Okay.